Mathematics is the search for patterns and for the explanations as to why those patterns exist. We see these structures everywhere, from the petals of a flower to the movement of the stars. To study these patterns, we look at number sequences. A sequence is a list of numbers that follows a specific rule to determine what comes next. This diagram shows the difference between the numbers in a list and their underlying rule. For counting numbers, the rule is a jump of +1. For even or odd numbers, the rule is a jump of +2. When you identify the rule, you can predict every future number in the sequence indefinitely. Numbers can be visualized as physical shapes. The square numbers are a clear example of this relationship. Look at how these dots arrange themselves. 1, 4, 9, and 16 are called square numbers because they form perfect equal-sided grids. We can do the same with triangular numbers, which follow the same stacking logic you see in bowling pins or billiards. This diagram shows that the rule for triangular numbers involves a growing jump. To keep the shape triangular, each new row must be one dot larger than the one above it, adding 2, then 3, then 4. Sequence rules can also be based on the relationship between neighboring numbers, as seen in the Virahonka sequence. In this sequence, every new number is the sum of the two numbers right before it. 3 plus 5 gives us 8, and 5 plus 8 gives us 13. These rules provide a framework for describing both geometric expansion and complex numerical relationships. Let's look at what happens when we add up consecutive odd numbers, starting from 1. Adding the first two odd numbers, 1 and 3, gives us 4. 3 new dots form an L shape around the first dot, creating a 2 by 2 square. If we add 5, the dots wrap around to form a 3 by 3 grid. The total is 9. This geometric rule allows us to calculate large sums instantly. To find the sum of the first 100 odd numbers, you simply calculate the area of a 100 by 100 square, which is 10,000. We can also find square numbers by adding counting numbers in an up and down sequence, such as 1 plus 2 plus 1. This chart shows that the staircase pattern of rising and falling numbers totals to the same value as a square grid. This alignment shows that the same numerical logic governs both the arithmetic sum and the physical shape. We can escalate this logic to even more complex shapes, like hexagonal numbers. This diagram reveals the rule for hexagons. We start with one dot and add rings of dots in multiples of 6. The jumps of 6, 12, and 18 show a pattern growing within the sequence itself. Recognizing these foundational rules allows us to categorize and use sequences efficiently. Here is our framework. Triangular numbers add growing bases. Square numbers are equal grids. Summing odd numbers builds those squares, and the Virahonka sequence sums neighboring terms. By identifying the explanations for these patterns, we can apply the same logic to solve problems in architecture, technology, and science.